Hello everybody. So this is gonna be a video for practicing the concepts that we have been discussing in the previous videos. We are discussing this example where we will try to do some calculations to apply the concepts and understand how we can use it to solve real problems. So this is a problem that is about liquid stripping. And stripping is a very well-known mass transfer process where a component in the liquid phase is transferred from the liquid phase to a gas phase. So by just mentioning that this is a stripping process, it tells us a lot about the direction of flow or direction of mass transfer, and consequently the gradients of the concentration or the profile of the concentrations in the liquid and the gas phases, just by knowing that this is a stripping process. So the maximum concentration is going to be in the bulk of the liquid phase. It's lower in the interface between the gas and the liquid, and it's very low in the gas phase or the bulk of the gas phase. So this is what we can understand from the word liquid stripping. In this problem, it's giving more details. It's saying that it's used to transfer hydrogen sulfide. So this is the solute or the species that is diffusing, dissolved in water into contacting airstream. So it's confirming the same information here, and adding that the solvent is water and the solute or the species A is H2S, and it says that the solvent, water, and the carrier gas, air, are assumed to be immiscible, which means that air is not dissolving in water, and so air is not diffusing, or there is no mass transfer for the air, and the solvent is assumed to be non-volatile, which means that water is not evaporating at the operating conditions. So it means that there is no mass transfer for water or for air, so mass transfer is only for H2S. This is the message that this sentence is trying to deliver. It says at the present conditions of operation. This is the important part here, or one of the important parts here, is to understand the inputs well. So it says that the mole fraction of H2S. So the first is that stripping process. The second is that the mole fraction of H2S in the bulk gas phase is 0.01. So this is Ya, the mole fraction in the gas phase, and in the liquid phase is 6 multiplied by 10 power minus 5. So this is the mole fraction in the liquid phase. We know that the individual mass transfer coefficients Kx and Ky are the given values here. So you can see that the inputs are in units of mole fraction for the concentrations and for the mass transfer coefficients. The statement of the problem says that the temperature is 20 degrees Celsius and the pressure is 1.5 atmosphere. The density of liquid approaches the density of liquid water at 20 degrees Celsius. So this sentence is important, and we're gonna use it later. But I'm not gonna discuss it right now because I want to keep it till the point where we will need it. But just keep in mind that the density of liquid approaches the density of liquid water, which means that the concentration is or H2S in water is low, so it's not affecting the total concentration or the total density of water. So this is like another wording of this sentence. Here we have the information about the equilibrium relation, which is the equilibrium line for H2S water air system at 20 degrees Celsius is found to obey Henry's law. So this is the Henry's constant. And in this case, we know that Henry's law is pressure equals H multiplied by concentration, and this can be confirmed from the units. And this is one very important thing here, that you have to keep an eye on the units to understand what is the constant that you have, the units of the two parameters that this constant is relating. So this is atmosphere meter cube per gram mole. So this is pressure divided by concentration. So it confirms that this Henry constant is not for mole fractions like what we saw before. Or the inputs that we have here. The molecular weight of H2S is given, and we need to calculate the liquid and gas phase interfacial concentration of ammonia. The overall mass transfer coefficients KL, KG, KX, and KY, the star variable CA star, PA star, and the mass transfer flux. So what we're gonna do is we're gonna solve this problem, and actually any method is gonna be enough or suitable to solve this. So we can solve it numerically, we can solve it graphically, we can solve it using the units of mole fractions, we can use the units of concentrations to fit with the Henry's constant. So we have different options, and actually what I'm gonna do is I'm gonna use almost all these options just to demonstrate that they all do the same thing. And this is one very important point, that you have to understand that if you're using the units of or the parameters of mole fractions, it's the same as using the parameters of concentrations and pressures regarding the final answer. So the final output that you're gonna get is the same in both cases. Of course, you have to do some manipulations to the units to make sure that the units are homogeneous and you're using the proper units for the system that you are dealing with, but at the end of the day, the output is gonna be the same. Either you use the units of concentration, pressure, or mole fractions, either you use the graphical solution or the numerical solution. So we have four alternatives, two for mole fractions and two for concentration and pressure. One is graphical and one is numerical. So this is what we're gonna do. This is way more than what is done in the textbook. So I did this intentionally just to confirm to you that it's the same. So the first thing, this is what I like to do actually, is to put the data that we have so that I don't need to go every time to the problem statement and see what the information I'm looking for. So I put all the information, the pressure, the temperature, and also it's helpful because you put everything in the proper symbols. So you take the time to list all the information that you have with the proper units, with the proper symbols, with everything, so that you can use them without having any issues. Sometimes it's somehow tricky or confusing to go to the text and then get a data and then go back to the solution. So I like to get this step done in the very beginning. I put all the information that I have here, and then I just put H in the units of meter cube, kilomole, and atmosphere, because these are the same units of kx and ky, just to make it easy for me. The second step is to put the profile, and this is very, very helpful to me because the absorption is different from stripping. It's the other way. The flow is going the other way, so the profile is flipped. So you have to make sure that you understand the driving force well. You understand what is greater. Is it the bulk in the liquid phase or the bulk in the gas phase? And this is really, really helpful when you do both the graphical solution and the numerical solution. So I like to do this as well here. So I'm done with these two, and now the next step is to unify the units. So I have to make sure that the units that I'm using are homogeneous. We said that the units of concentrations and the mass transfer coefficients, as we see here, they are all homogeneous, but the equilibrium relation is not homogeneous with them. So this is not y equals mx. So I have one of two options, either to change these to be in the units of pressure and concentration, or to change this constant to be in the units of mole fraction. So I'm gonna do both. So let's say I'm gonna use the units of mole fraction. So x, y, k, x, and ky are already fine. I don't have to do anything for them. Now the next is the only parameter that needs to be fixed is the equilibrium constant. And to do this, you have to rearrange the equation. So the equation is P equal H multiplied by C. This is the equilibrium relation that we have here. We can assume that this is an ideal gas because we are operating at low pressure. So we say that it's Y multiplied by total pressure. This is Dalton's law. And we say that this concentration is the mole fraction multiplied by the total liquid concentration. And then we can rearrange the equation to be Y equals HCl divided by P multiplied by X equals MXA. So this is the equilibrium relation. This is simply the equilibrium relation now is Y equals MX. So if I can calculate the value of M, then I'm done. To calculate the value of M, I need H, Cl, and P. I know H, it's already here. P is known, it's 1.5 atmosphere. So I need to know Cl. So Cl, as you know, is the total liquid concentration, or the total molar liquid concentration, which is the total number of moles of liquid over the volume of the liquid. And to do this, and of course this is dependent on the components that we have in the mixture. So we have water and we have H2S, but we will, and of course it's going to be tricky to do these calculations for a binary mixture, and that's why we had this sentence here that the density of the liquid approaches the density of liquid water at 20 degrees Celsius. So it means that the concentration of H2S is very, very low, so that it's not affecting the density of the liquid water. And we can make a very good use of this to say that the liquid concentration is the total number of moles divided by the volume, and we can say that this is the number of moles of water because H2S is very, very small amount, it's very negligible, and you see here it's 6 multiplied by 10 power minus 5. This is the mole fraction, and we know N equals the mass divided by the molecular weight, and then mass of water divided by V is the density of water divided by the molecular weight of water. So we can calculate the total liquid concentration as the density of water divided by its molecular weight. So this is the total liquid concentration. So now we can directly substitute in this relation to get the value of M. And now, of course, M is dimensionless because it's a ratio between two mole fractions. And if you can check the units of HCl and P, it's gonna be dimensionless as well. So these are the information that we need to know if we are using the units of mole fraction. The other option is to keep H as it is and change the units of concentrations XY to be K to be C and P, and KX and KY to KL and KG. And of course, this is more lengthy process because you have to change the units of 4 parameters instead of just one in the previous case. But again, just to show you that all the options are valid. So for the flux equation, to get the relation between KL and KX, I always like to do this. I know it might be kind of repetitive, but just to make sure that I don't make mistakes, what I do is I simply write the equation using the two mass transfer coefficients. So it's KL multiplied by CL minus C interface, and that's why this profile here is important now. It's KL multiplied by CL minus C interface, or KX multiplied by XA minus AXA interface. And here I can put XA as CA divided by CL and the XA interface as C interface divided by CL, and take CL as a common factor, and from these two, this and this, I can tell that KL equals KX divided by CL. I don't memorize these kind of equations. I like to get them or derive them each time I use them because sometimes it confuses me. So I like to go simply with this very quick derivation. So I can say that KL equals KX divided by CL. I know KX and I know CL, which I got from here. So I now can calculate the value of KL, and the same for KG. I can say that KG multiplied by delta P equals KY multiplied by P divided by total pressure minus P divided by total pressure, which is KY divided by P if I take P as a common factor, and we did this before. So now you can say that KG equals KY divided by P, which is this value. For the concentration and pressure, it's very easy. You can use the same equations that we use here, Dalton's law and the X divided by total concentration, to get the concentration of liquid and the partial pressure in the gas phase. So now we have all the parameters in the units of concentration, pressure for all the parameters. Now we can solve the problem once using the graphical solution using these parameters, or once using the graphical solution using these parameters, or numerically here and numerically here. So we will see the 4 options. So for the first option, if you use the values or the units of mole fractions, then we have the liquid mole fraction and the gas mole fraction here. And again, this is something that I really encourage you to do if you do this kind of problems, is to solve them manually. You have to take a pen and or a pencil and a piece of paper, draw the graph, and understand how to make the scaling and to do the drawing. It seems simple, but if you do it, and I confirm this to you from my experience with the students. It sounds very simple and very easy to do, but when you go to the real application, or you do this by yourself, it gets really tricky. In many ways, or in many steps, in adjusting the scale for x-axis, for y-axis, it's very tricky. To draw the lines and to draw the straight line, believe me, it seems very simple, but a majority of the students fail to do this from the first time. So you have to try and make mistakes and then understand how to do it yourself. So now we have here the point, which is xa, ya, which is this point, and then we know that the slope is negative kx over ky, so we can draw a straight line with a slope of negative kx and ky, which is the mole balance equation. And then the intersection point is gonna be x interface and y interface, and from this from the graph we can tell that the interfacial concentration in x and y is 3.6 times 10 power minus 5, and it's almost 0.0118 for the gas phase. We can also get the star variables, which is c star, x star, and y star, which can be found from the graph to be, this is y star, which is less than 0.02, which is 0.0195, and here it's almost 3 point something times 10 power minus 5. So these are the values that you get. And again, just to make this point clear, the graphical solution, especially if you're doing this manually by your hand, it's not gonna give very accurate results compared to the numerical solution. The numerical solution is solution of equations together, so you get really accurate values. Here it gets you good values that might not be very accurate, and that's why you might get some differences between the values that you get here and you get from the graphical, the numerical solution. We can repeat the same graphical solution using the units of pressure and concentration. Here the concentration is in gram mole per meter cube, the pressure is in atmosphere, and here is the point of CAL and PA, which is this and this. And again, we will draw a line with the slope of negative KL over KG, and this is the operating line. Now the intersection is C interface and P interface. We can get the values from the graph. If you convert these into mole fractions, meaning that you divide this by the total liquid concentration and divide this by the total pressure, they're going to give you the values that we got from the previous graphical solution. We can get the C star and P star, which as you see, these are the values of P star and C star from this point and this point. So this is like halfway the solution. We just need to get the overall mass transfer coefficients and the flux after this, but we need to get these values first and then go to the next. Before we proceed, I would like to repeat the same solution using the numerical solution. So I have here all the parameters that I have for KL, KX, KY on all the units of mass transfer and all the units of concentrations and pressures and mole fractions to be suitable for the solution. So I'm gonna do the solution first using the pressure concentrations. So this is the balance equation, this is the equilibrium relation. So what we did in the graphical solution is we got the intersection of the the operating line, or the mole fraction, mole balance line, and the equilibrium line. So this is what we'll do here. We'll solve these two equations simultaneously. We can combine the equations, solve them simultaneously. All what I did is I just put P interface as HC interface, which is this. I'm sorry, which is this. So this is HC interface. So I'm rearranging the equation to make sure that I have C interface as a function of the rest of the parameters. So this is C interface. I know everything else, so I can directly substitute in the equation to get the C interface, and then you can substitute either here or here to get the P interface. So you can get P interface as this value. So this is the exact solution that we did before. We can or the graphical method, but this is the numerical method. Again, it's giving very close, if not the same values that we got before. We can repeat the same for mole fractions. Again, I have the equilibrium relation. We are repeating the same steps, solving the two equations simultaneously to get X interface and Y interface. So I'm not wasting time. I just want to confirm to you that this is the same. So I might you might feel that this is repetitive or I'm wasting time, but I'm doing this based on my experience with the students. They fail to understand that the two methods are the same, so I'm trying to make it clear for you as much as I can. Now to go for the overall mass transfer coefficients, we can use this relation, which is 1 over kg equal 1 over kg plus 1 over h over kl. And again, this is a valid equation only in case of having a linear equilibrium relation. If you have a nonlinear equilibrium relation, this is not going to be valid. So I want this point to be clear. So you can do this for Kg, Kl, just a direct substitution in the equation. You can get P star from the equilibrium relation. This is what we did in the graphical solution. Again, it's giving the same results. You can do the same for mole fractions. This is Ky, this is Kx from the relations. And then you can get y star and x star. Finally, we need to get the flux or to get the relative resistance first. So to get the relative resistance, we have already the overall mass transfer coefficients and we have the individual. So we can say that the relative resistance in the liquid phase is KL divided by the overall KL divided by the individual KL, which is 83%, and the same for KG. And of course, the summation of these two should be 100%. And the same results are got from the mole fractions in the or the calculation using the mole fraction. So either way is gonna give the same results, which confirms that both are the same. Finally, to get the flux, we have different options. We can use individual mass transfer coefficients. You have overall mass transfer coefficient. You can use it for mole fraction. You can use it for concentrations and pressures, and that's why we have different options. We have 8 ways to calculate the flux, and I put all of the possible equations that we can use to calculate the flux here, and the flux in using all the methods is the same. The value is the same. So if you use Kx, which is the individual in the liquid phase and the individual in the gas phase, overall in the liquid phase, overall in the gas phase, or for mole fractions, or for concentrations and pressures, they are all giving the exact same values. I have put all the parameters that we are using here just to make it easy for you to pick the values and use them. But at the end of the day, the output is the same. Of course, you are not requested to do this or use the 8 equations, but I'm doing this again just to show you that whatever the method that you're gonna use is gonna be right and is gonna give the same output. So this is all for this problem. In the next problem we will solve, or next video we'll solve another problem which is kind of similar but with some differences. So I'll say it then, inshallah. Goodbye.